In earlier courses, we presented gravimetry, the traditional measurement of gravitational field strength. In this course, we will be discussing gravity gradiometry, the measurement of the rate of change of gravitational acceleration. Gradiometry measurements calculate the gravity gradient. This gradient utilizes three primary planes to determine the spatial rate of change of gravitational acceleration. The three component vectors of the gravity gradient are gx, gy, and gz. The most intuitive component is the vertical gravity gradient, gzz, which is the rate of change of vertical gravity, gz, with height, z. This is measured using two vertically separated points, for example, gxz1 and gxz2. The value of gravity at the 2 points is differenced and divided by the vertical distance between them. Accelerometers are used to measure the gravity gradient. These are contained within gravity meters that are typically located in or on moving vehicles, such as airplanes or ships. Full tensor gradiometers, FTG, produce the gravity gradient tensor. This is comprised of a total of 9 gravity gradients that provide a better understanding of the noise and acceleration sources of the gravity data. These gradients help process 3D effects outside the plane of the survey line. To explore FTG application to oil and gas operations, we'll take a brief look at data in the K2 field. In this area, imaging beneath salt is extremely important to determine both the size of the field and to assess for future drilling targets. Normal pre-stack depth migration of seismic data in this area has provided adequate salt mapping for the base of salt where the salt structure is tabular. This is shown by good subsalt reflections in the southwest portion of this section. However, no continuous subsalt reflections are visible in the northeast portion. To help map the base of the salt in the northeast portion, FTG data was acquired. This image is from conventional gravity data, comprised of the vertical derivative of the vertical gravity component. These images are from FTG data and clearly provide much better resolution. With better definition of the salt in this section, the seismic was reprocessed using wave equation pre-stack depth migration. As you can see, the subsalt imaging has been significantly improved in the northeast portion, and we are now able to better identify the position of the bottom of salt obtained from the inversion of FTG data. This example illustrates how pre-stack depth migrated seismic data, gravity gradiometry data, and well information can be used to enhance our understanding of the subsurface. Time-lapse gravimetry can provide independent information about the mass redistribution of fluids that occur in a reservoir during production. This process involves repeated absolute gravity measurements at specific survey points, which can be combined into an overall gravity profile. Time-lapse gravimetry is more effective when applied to reservoirs that contain fluids with high-density contrasts and have a large size-to-depth relation. Additional applications of time-lapse surveys are presented in the course content. Gravity gradiometry has many advantages, some of which are listed here. The primary disadvantage of the gravity gradient is that the absolute gravity value may not be as accurate as other techniques. Actual gravity measurements are more sensitive to regional signals and deeper sources, both of which are longer wavelengths and have much slower changes in gradients. This video has provided an overview of gravity gradiometry, its advantages and disadvantages, an application of full tensor gradiometers, and an introduction to time-lapse gravimetry. Further details on these subjects are provided in the course content.